Hello, I think I'm live, so just please let me know in the chat that you can hear me well and that you can see the screen so I can start today's lecture on convolutional neural networks. So there might be, I don't know, maybe a higher delay I saw today, but no, it seems to be fine. Okay, thank you. Okay, so as I said, today we're going to discuss about convolutional neural networks. So this is a specific neural network architecture that is based on deep learning and also on some specific layers. So today we're going to discuss about different convolutional neural network architectures and see the components in these architectures and try to decipher the way it works. So just a short recap from last time. So we know that neural networks are trained using mini-batch stochastic gradient descent, which is based on taking a random selection of data samples for a mini batch. These are passed through the network using forward propagation of the input to get some output probabilities and obtain a value for the loss function. Then we backpropagate the gradients using the chain rule, and then we update the parameters based on the computed gradients. So we're still using feed-forward architectures. So the convolutional neural networks are trained in exactly the same way as feed-forward neural networks. Okay, so I'm not sure that I mentioned this before, but neural networks are universal function approximators. Maybe I mentioned it, but I didn't show you the universal approximation theorem that states that a feed-forward neural network with at least one hidden layer that is composed of a finite number of neurons can approximate any continuous function on a compact subset of the Euclidean space of n dimensions. So yeah, the idea is that having a compact subset is just a Cartesian product of intervals. So you can think of just maybe select a portion of this Euclidean space that is continuous, and this is a compact subset. And then any decision boundary that goes through this compact subset can be approximated with a neural network with only two layers, so it is sufficient. So this theorem is very powerful because it tells us that we can use neural networks to learn basically any decision boundary. And although this happens in theory according to this theorem, the problem is that the hidden layer's width, I mean the number of neurons on this layer, can be exponentially large. So in order to avoid, so for very complex problems and realistic scenarios, such networks are very hard to train, very hard, because the exponential number of neurons that are needed with respect to the size of the input. So there are some results, not only practical results, but also some theoretical results that show that deeper networks with fewer neurons are equivalent with shallower networks with an exponentially higher number of neurons. So in order to reduce actually the number of neurons that are required and to be able to train the models, we prefer to increase the number of layers and to use less neurons on each layer. And yeah, this is maybe this theory was developed a bit later than the practice. So people started using deep neural models in practice and observed that they obtain improved results. And they also asked why does this happen, and they tried to find different explanations. So in deeper models, we are able to learn more complex functions that model the reality better than trying to use a shallower network that needs a lot of neurons to model the same complexity. Okay, so last time we also discussed about dropout, a method that can be used as a type of regularization. So actually this was introduced as an approach to regularize deep convolutional neural networks. So we can say that in some way we already started a discussion about convolutional neural networks last time. So yeah, just quick recall that dropout is this idea to drop some of the units from the network during the forward and backward passes, and the units are that are dropped out are always selected randomly with each mini batch. And this improves the model capacity by building a redundant representation of the data. Okay, so now about convolutional neural networks. This type of architecture was introduced in 1998 by Jan LeCun. So this was the LeNet architecture. So actually, sorry, here the time is wrong, so it should be 1998. And yeah, this architecture was proposed by Jan LeCun and his co-authors for the MNIST database, and the name of the architecture comes from his name, LeCun, and they called it LeNet. But this was the name of LeNet appeared later than the paper was proposed. Yeah, so here we see these feed forward. We see this feed forward architecture with these operations, convolutions, and subsampling. And here we see some layers. So these are fully connected layers. And actually, in order to better understand this architecture and notations, we are going to discuss the details next. So first we discuss about the convolution layer, which is the central component in a convolutional neural network. So this gives the name of the network. So the convolutional layer is mainly applied or is mainly useful for images, and it is inspired by the human visual cortex. So it is naturally designed for images, but it was later applied also on text and other type of data. Okay, so in the convolutional layer we have an input, and in this case we have an input image of 32 by 32 pixels that has 3 channels, red, green, and blue. So the depth is equal to 3. So in the convolutional layer we have convolutional filters. So we have this filter that is convolved over the image, which means that we slide the filter over every possible spatial location and apply the convolution operation, which is based on multiplying the components inside the filter with the components inside the location where the filter is applied, and the result is a single number that is the output for this filter. Okay, so the first observation is that the convolutional filters always extend, at least in standard architecture, they always extend the full depth of the input volume. So here we have 3 channels RGB, and the convolutional filters are applied on all 3 channels at once. And the result of the convolution operation, as I said before, is a single number. So this is equivalent with multiplying some part of the input. So this input here from the pink tensor is X, and the weights, the components inside the filter are W. The filter also has a bias term B, and the output is computed by multiplying the weights with the input X, and this multiplication is component-wise or element-wise, so it's not standard multiplication. And the result is a single number, which is the output of applying this filter in this location. So since we apply the filter in every possible location over this image, we obtain an activation map, which is formed of all the outputs resulted from applying the filter in every location. And in this case, we have so the notice that the activation map has depth of 1, and actually in a convolutional layer we have more convolutional filters. So usually we can have, I don't know, 6, 10, 32, even 500 or 1000 filters. So for each filter we obtain a different activation map. So here from this input tensor we obtain an output tensor that has the spatial size is proportional to the spatial size of the input. We are going to discuss later on how this how exactly we obtain the spatial dimension. And the number of filters here gives us the size, the depth of the output. So for example, if we have 6 convolutional filters, here we obtain 6 activation maps. So this results in a tensor of 28 by 28 by 6. And then when we apply another convolutional layer here, our filters will span. So the convolutional filters that are applied on this input tensor have the same depth as the input. So they have the size 5 by 5 by 6. So here the size, whether it's 5 by 5 or 3 by 3, it can be chosen. It's a parameter of the model, and it has to be an odd number. This is because just in usual convolution we use an odd number for the input, and this is done because we want the number that we obtain as output to correspond to the central location of the input, the center of the input. Okay, so yeah, usually in the neural architectures we increase the numbers of filters with the depth, and this is because in the visual cortex we have a similar structure with a few neurons that activate. Actually, maybe this will be discussed better on this slide. So yeah, we need fewer filters that activate on low-level features such as bars, edges, stains, and so on. So bars with various orientations and corners and so on. And then for the mid-level features, we start to build more complex parts, like here we have some corners, some texture patterns, and so on, until the high level features we have object parts. So here we have the head of a bird, the wheel of a car. I don't know, maybe this looks like a window or something. Yeah, different patterns, different textures, some square object here, and so on. So here, since these filters are common for all object classes, so we expect edges and the corners and so on for different object classes. We don't need as many filters as in this layer, and here the filters are more specialized to various object classes. And if we have a lot of classes to discriminate, as in the ImageNet database with over 1000 classes, we need a lot of filters to in this layer of the network. Okay, so one important aspect here is to notice that these filters are actually learned from data. So the weights here, the weights W inside the filter are actually, so this filter is actually interpreted as a neuron, and the weights are the learnable parameters of the convolutional layer. So what is shown here is not filters that are handcrafted into the architecture. These are learned from data. So we just need to define the structure. So I need a layer with, let's say, 6 filters with 5x5 spatial support, and then the filters are automatically learned from data. And here we see some examples on, so this is an input image, some filters that are learned from the data, and the corresponding activation maps. So the activation maps emphasize the patterns of the filter. So if the input image correlates well to the shape of the filter, we will see higher activations here. So the activation maps really emphasize the patterns that are contained in the filter. So here, for example, we have a stain pattern. So this emphasizes stains in the image, and this emphasizes maybe bars that are oriented like this. Here we have also bars that are oriented like this but are slightly thinner, and so on. So here I see some vertical patterns. So perhaps this belongs to, let's see, 1 2 3 4 5, 1 2 3 4 5. So this pattern here corresponds to this image, and yeah, and so on. So these are the activation maps, and these are the filters that are applied on the input image. And you can see that the filters emphasize the corresponding patterns. So we can understand this better if we look at this one-dimensional convolution operation, and this shows how the convolution is applied actually on a one-dimensional signal. So the same thing happens on images that are 2D. So here this filter with red is convolved over the signal f, and the output is depicted with black. So when we multiply here the signal f, which is 0. With the filter, we obtain the output is 0. And when we have some overlap, we obtain a higher activations, and when they have this perfect overlap, we obtain the highest activation of the filter. So the output activates where the filter is similar to the input image, and yeah, it is proportional to how similar it is with the input image, of course. And this is what happens in 2D, and the same happens in this is what happens in 1D, and the same happens in a two-dimensional space. Okay, so the typical CNN architecture has convolutional layers and ReLU, convolution, ReLU, and there are also these pooling layers that are we're going to introduce next. But I just want to observe here that after a convolutional layer, so we have these activations. So notice that here we can also have negative correlations. So actually here we only have a positive input, but we can also have, so the filters can also have negative values. So the weights can be positive, but they can also be negative. So we can also have negative activations. So here we usually apply ReLU or similar activation functions that removes the negative activations of these filters. And this is also correlated to what happens in the human visual cortex. So because we identify, well, this happens subconsciously. We're not thinking about identifying edges and corners. This happens automatically inside the visual cortex when we look at objects. But the main idea is when we are trying to identify an object, we are not thinking about the negative activation. So imagine that we apply, let's say, this filter with a bird, and when we want to identify birds, we get this activation where we see a bird head, but we do not think about the negative activations for the other filters, such as, I don't know, so when you look, let's say, at the bird, you're not thinking about, or the brain is not thinking that this is not a car, this is not a person, this is not I don't know, a plant, it is a bird. So yeah, it's not Superman. Okay, so the main idea is we want to keep only the positive activations by applying ReLU activation, which we discussed in the previous lecture. So and yeah, the convolutional neural network can also have fully connected layers, which we discussed actually in the previous lecture, so we're not going to go too much into these details. We are going to finish the discussion with convolutional layers and then go to discuss about the pooling layers, which are quite easy to figure out. Okay, so first, how we determine the size of the activation map. So in order to be able to design convolutional neural networks architectures, we need to be aware of the size of the activation maps and to know how many convolutional layers we need to add, and when to add pooling layers, and so on. So and the example that I showed before, if we apply the convolutional filter in every possible location over the input image, we obtain an activation map of 28 by 28 components. So why does this happen? So let's take an easier example with an input of 7 by 7 pixels and a filter of 3 by 3 pixels. So when we apply this filter on top of this image, in every possible location. On one dimension, we obtain an output of 5 by 5 components. And yeah, so I'm trying to go for a more generic formula that also includes the stride. So one thing that I didn't mention before is that we can also apply the filters using not in every possible location, but skipping a number of pixels. And the number of pixels that we keep is commonly called stride. So here, if we use stride 2, it means that we skip 2 pixels, and then we apply the filter again, and then we skip another 2 pixels and we apply the filter again. So in this case, the filter is applied 3 times. So the corresponding output will have 3 by 3 pixels. So what happens if we want to use a stride equal to 3? We cannot fit it exactly, so we cannot apply a 3 by 3 filter on an image of 7 by 7 pixels using a stride 3. This is because in this case the filter will not apply. So okay, so the formula so far in order to determine the size of the input is equal to the size of the input n minus the size of the filter divided by the stride plus 1. So in the previous examples, if we use a stride 1, we know that the output has 5 by 5 pixels. If the stride is 2, the output will have 3 by 3 pixels. And if the stride is 3, we cannot divide exactly here this 4 by 3. So this is not a valid configuration of the convolutional layer. However, what we can do in order to be able to use any stride that we want, we can add a border around the input image with zeros, which allows us first to use any stride that we want. We just need to make sure that we can apply the filter in every possible location, so we get a division, a correct division. And another utility is that if we want to obtain an output of the same size as the input, then we can control this by adding this border. And this parameter is typically called padding. So if we pad the output with a border of 1 pixel, we obtain an output of 7 by 7 pixels in this case. So we obtain the output as the same size as the input. Okay, so in general, if we want to see conv layers with stride 1 and filter size of f by f, and we want to preserve the size, so we just need to add zero padding with the size of the filter minus 1 divided by 2. So if the filter size is 3, we need to add a padding of 1 pixel, so 3 minus 1 divided by 2 is equal to 1. If the filter size is 5, we need to zero pad the input with 2 pixels, so 4 minus 1 divided by 2 is equal to, and so on. Okay, so as I said before, this is useful because if we do not add this zero padding around the input, the spatial dimension decreases too fast, and we are limited with respect to the number of convolutional layers that we can use. So we want to control this by adding zero padding. And yeah, now we have some exercises for you to make sure that you got these ideas correctly. So the first question is given an input volume of 32 by 32 by 3 components and a convolutional layer with 10 filters of 5 by 5 spatial support that are applied with a stride of 1 and a padding of 2. So what would be the size of the output in this case? Okay, I'm not going to ask you about the explanation, just to give me the size of the output, and I will consider that as a good answer. Yeah, so I see questions here that yeah, the course is always at the same time every week. For those interested that are outside our university. Yeah. Okay, so yeah, we have a good result from Rafael. Thank you for the answer. So indeed, the output volume is 32 by 32 by 10. And how is this computed? It is based on the formula that I showed you before. So the size of the input, and in this case, the size of the input is 32 plus the zero padding that goes in both sides of the input image. So it 2 times the padding, which is 2. So the size of the input is actually 36. Minus the size of the filters, 31, divided by 1 plus 1, we get the output 32. And this was actually also, you can also figure this out based on the effect that I said. When you use 5 by 5 filters, you need a padding of 2 in order to make sure that the spatial volume is of the same size as the input. And the depth is given by the number of filters. So I mentioned that we have 10 filters. So we have 10 activation maps. So this is the size of the output volume. So the answer of Rafael was correct. And now another question is, what is the number of parameters in this layer? So you will see, we'll also discuss about the number of parameters in a convolutional layer and the number of parameters in a fully connected layers that would be necessary to simulate the same process. So yeah, the question is, what is the number of parameters in this layer? So the parameters are the components of the filters that are learned, and you have to consider all the filters and also include the bias terms in order to answer this question, because the parameters are also learnable. Okay, so the first answer is not correct. 5 by 5 by 10 is not correct answer. You're forgetting, yeah, you're forgetting perhaps the third dimension, yeah. And we have a close answer from Rafael, and which I think it misses the bias terms. 5 by 5 by 10, no, Catalin is also wrong. So he added the bias terms but didn't consider the spatial dimension. Okay, yeah, so Rafael is once again correct. So yeah, as I mentioned, so now I observed that Rafael already gave 2 good answers, so I'll please ask him not to answer to the following questions and to leave others to provide the answer, or because you're allowed to maximum of 2 answers per lecture. Okay, so The number of parameters is 760. So recall that each filter spans the entire depth of the input. So the input has a depth of 3. So the filters are 5 by 5 by 3. And there is also the bias term. So each filter has 76 parameters, and we have 10 filters, so the total number of parameters is 760. Okay, so this summarizes the discussion about parameterizing convolutional layers. So typical values for the number of kernels are 16, 32, 64. So we usually use powers of 2, but this is not, so it's like more of a practical choice than a theoretical motivation to do it. So you can use any number of parameters, any number of kernels. It's not necessarily you have to use powers of 2. Then for the filter size, we in the modern architectures we commonly use filters of 3 by 3 or 5 by 5 or even 1 by 1. And the padding is set in order to make sure that the filters fit on the image, and stride can be 1 or can be even higher than 1, depends on the how many layers you want to include in the architecture and so on. So yeah, we're going to discuss more of some architectures that were proposed in literature and are very famous, and you will see how these are configured. Okay, so one observation is that it also makes sense to use convolutional layers of 1 by 1 spatial dimension, and this is because the filters span the entire size, the entire depth of the input. So it means that for an input that has 56 by 56 by 64 components, the 1 by 1 convolutional filters will also have depth of 64. So and the output will be only one component. So it makes complete sense to be like that. Okay, I remembered. Yeah, I don't have any more slides for that, but I remembered one thing that I wanted to mention. Maybe here, yeah. So one important thing is to maybe to understand how these filters are combined into more complex filters. And how this happens is that when we apply these low-level filters and extract here activation maps that correspond, I don't know, to edges with various orientation, so assuming that here we have 2 activation maps and one that activates on vertical bars and another one that activates on horizontal bars. When we apply here a convolutional filters on top of these bars, the filter will see both the activation for the vertical bar and the horizontal bar in the same location, of course in different activation maps, but at the same location. So this filter can learn to combine these bars into another filter, and the filter can now activate on corners, like, so it combines a vertical bar with a horizontal bar, and you can learn to activate on corners that are I don't know, perpendicular to the ground. So yeah, just so the main idea is how these are combined is based on the fact that the convolutional filters from I don't know, the convolutional layer I are applied on the on all the activation maps at once from the previous layer I minus 1. So these filters are able to combine the activations from the previous filters into a single filter. So actually you can obtain any combination from the previous layer. And this happens here as well, and so on. So you get more and more complex features and filters as you increase the depth of the network, the number of layers. Okay, so this was one important aspect for you to understand how these features are constructed. So now going back to I think we were on this slide. So checking the time. So I think maybe, yeah, maybe I need to move a bit faster. But yeah, there is also a connection with the neurons in the brain. So we can interpret this filter as a neuron that has local connections. So the neuron is only connected to this. So this can be seen as the output from a previous layer. So every number is an output. And in a fully connected network, every number here will be connected to each neuron. So the number of parameters and the number of weights will be much higher if we consider all the possible connections. And here for the convolutional layer, we have only local connections. So this neuron is connected only to this part of the input. And another constraint is that this same neuron is applied on different locations on the input image, and the weights are always the same. So the same neuron with the same weights is applied in different locations, and this is a constraint that further reduces the number of parameters. And in one location, so we can interpret the activation map as a sheet of neuron outputs, and yeah, each pixel or each component in this activation map is a different neuron, but these neurons share the same weights, so they have the same parameters in every location. So it's a much more efficient way to connect the output from the previous layer to the current layer of neurons. Okay, and in every location, so we have different filters. So we just, each filter is a different neuron. So it's just assuming that the neurons are arranged in this three-dimensional grid. Okay, so yeah, this is the correspondent between fully connected layers and convolutional layers. Okay, so this was the final observation for the convolutional layers. So now we move to the pooling layers. So the pooling operation is based on making sure that the representations are reduced and in terms of space, so the spatial dimension is reduced, and they also become more manageable. So as we increase the number of as we need to increase the number of filters in the latter convolutional layers, we also need to decrease the size of the activation maps, the spatial size, but we want to control it and to make sure that we do this exactly where we want it. So this is why we use pooling layers. So as you can notice here, this is the input for a pooling layer, and this is the corresponding output. We just decrease the spatial dimension, and keep the same depth as the input. And this is what happens. So in this is the activation map here that is depicted as a 2D map here. And usually we want to keep the highest activations. So typically we apply max pooling, but there are also other operations that can be applied, like average pooling and so on. So with max pooling from each activation map, we have these pooling filters. So for example, in this case, we have filters of 2x2 components. So this is one location where we apply the filter, and we use a stride of 2. So this is another location where we apply the filter, and so on. And in each location, we take the maximum value and we keep it for the reduced map. So as you see here, we do not care actually. This gives us these sharp edges. We do not care about the sharp edges. We just care about keeping the maximum activation in the downsampled activation map. Okay, so this is applied on each activation map, and as I said, the number of activation maps is the same, just their size is decreased. And now we can decrease it. For example, in this case, we decrease it 2 times on each axis. If we use filters of 2x2 and a stride of 2, we can decrease it, I don't know, 3 times on each axis by using filters of 3x3 and a stride of 3, and so on. So typically we use pooling with 2x2 or 3x3 filters and a stride of 2 or 3. And these are the only parameters that need to be adjusted for the pooling layer. And yeah, as I mentioned before, the fully connected neurons are just in ordinary feed-forward neural networks. They have full connections with each other, and these are typically used before the softmax classification layer. Okay, so now we start discussing about some typical CNN architectures that were proposed in literature. So we start with the one that was introduced by Jan LeCun, the first CNN that was introduced in 1998. So this LeNet 5 has 5 layers. So the name comes also from the number of layers. And following our previous discussion, we can now understand how this specific architecture is designed. So here we see that the input is grayscale, and it has 32 by 32 components. So we know here that the filters, so we see that the output is 28 by 28, and the stride is 1. So at that time the stride was not a parameter and the padding was not a parameter. It was introduced later to better control the architecture, but here we have we have stride 1 and we don't have any padding. So here we know that actually in order to obtain these activation maps of 28 by 28 pixels, we know that the filters have 5 by 5 components. And we see here that in this image we have 6 activation maps, so we must have 6 filters in this convolutional layer. And then we have this subsampling operation, and this is actually a pooling layer. So initially it was called subsampling. And yeah, in this LeNet architecture, the subsampling was based on average pooling, not on max pooling. So max pooling was introduced later. But either way, we can see that the filters have a size of 2 by 2, and they are applied at a stride of 2. So this results in 6 activation maps of size 14 by 14. Then we have another convolutional layer with filters of 5 by 5. So here we see that the difference is 4. as same as here, so it must be that the filters are also 5 by 5. We have 16 filters, and then we have another subsampling layer, and we have 16 activation maps with 5 by 5 components. And then we have a fully connected layer with 120 units, then another one with 84 units, and finally the output layer with 10 classes from the MNIST database. Okay, so this is the architecture of LeNet. The next important architecture in literature is AlexNet. So this was introduced by Krzyzewski and Hinton when they participated in the ImageNet competition. So they proposed this architecture with 8 layers that was later named AlexNet. This is the first name of the first author, Alex Krzyzewski. So the input here is they used an input of 27 by 27 pixels. So all images in ImageNet were resized to this input size, and they used color images. So the depth is 3 pixels. So in the first layer, actually, when they trained the network, they trained it on a GPU that actually using 2 GPUs that didn't have too much video RAM. So they had to train actually 2 independent networks on each GPU, and then they concatenated the networks together. So here you see that one network has 48 components and the other one has also 48 filters, and these are stacked together into a single network with 96 filters. And the filters have 11 by 11 components, and they are applied at the stride of 4. So yeah, this is a nice exercise for you. So what is the size of the output for this architecture? So for AlexNet, we have here filters of 11 by 11. They are applied at the stride 4. We have 96 filters, and the input size it's 227 by 227 by 3. So what would be the size of the output volume? Waiting for answers. So just apply the formula from before. Okay, so we have an answer, 55 by 55 by 96, which I think is correct. Yeah, because the output volume is 216 divided by 215. No, it's 216, yeah, divided by 4, and then plus 1, we have 55. And yeah, the number of filters is, we know that it's 96, so the output volume must be 55 by 55 by 96. Okay, and the second question is, what is the number of parameters? So we now know you can actually provide a rough estimate because we have quite a few parameters. So you can either tell me the exact number or an estimate. Okay, so what is the total number of parameters in this first layer? So we have 96 filters, 11 by 11 components. So basically, yeah, if I ask for a rough estimate, you can ignore the bias terms. So yeah, waiting for the question. Okay, so 96 filters, 11 by 11 by 3. So a rough estimate would be probably 100, 300, around 30K. So yeah, that's the number of parameters, around 35 1000 parameters in this layer. So yeah, this is a much larger network compared to LeNet, and it also actually takes a lot more time to train on ImageNet. Yeah, so we can go on with the pooling layer, which has 3x3 filters that are applied at the stride of 2. So what would be the size of the output volume for this pooling layer? So the filters, the pooling filters have 3x3 components, and the stride is 2, and the input volume is 55 by 55 by 96. So yeah, this is a question for you. Okay, so Bogdan also provided 2 good answers, so I'll leave the other questions for the other students. So now I'll expect an answer for this question. So what is the size of the output volume after applying this second pooling layer? So just wait for a couple of minutes, maybe 1 or 2. So yeah, you can apply the same rule as for the convolutional layers in order to determine the spatial size. And before I mentioned also about the depth, so you can actually figure out the size, I think, quite easily. So I'm also trying to compute in the same time to figure out how much it takes. So okay, so I got it. So it's pretty fast to do. Okay, since I'm not seeing an answer, not to further delay, I'm going to give you the answer. So in this case, the hint is we can compute the size of the output volume using the same formula with conv. So the size of the output volume is 27. So the output volume is 27 by 27 by 96. So we keep the same number of activation maps, which is 96. And another question, which I think it is easier for you to answer. What is the number of parameters in the pooling layer? So yeah, I didn't mention it before, but it's a nice exercise to think about. What is the number of parameters that are learned in the pooling layer? So the number of weights. Okay, so we have a good answer from one student. So indeed, there are no parameters in this layer. So yeah, during optimization, it doesn't add any additional computations for weights. Okay, so yeah, if you take the whole architecture, you can compute and see the size of the activation maps and the configuration with the number of filters, the size of the filters, the stride padding, and so on. So yeah, this is the AlexNet architecture, and this architecture also inspired future architectures such as VGG. We're going to discuss next about VGG in more detail. Some important aspects is that this was the first use of rectified linear units in deep neural networks. They also used normalization layers, which are no longer used in more recent architectures. They used a lot of data augmentation to improve results. They also used dropout in in their network. They used the batch size of 128 images. They applied stochastic gradient descent with momentum using the momentum rate of 0.9. They started with a learning rate of 0.01, and they reduced the rate by 10 each time the validation accuracy reached a plateau. So in the end, they use an ensemble of 7 CNN models to obtain this top 5 error rate of 16%. And yeah, about the training time, which I mentioned earlier, it actually took them around 2 weeks to train this model on ImageNet. So ImageNet is a very large database, and it takes a lot of time to train neural networks. And larger models that are used today, like ResNet, they actually are more heavy to train. So they are larger models that require actually also 2 weeks. But this is done using machines with 8 GPUs in parallel. So it's quite complex. Okay, so next we discuss about VGG. So the after the introduction of AlexNet, the visual geometry group from Oxford proposed this network, which got its nickname from the group from Oxford, the visual geometry group, so short VGG. And this architecture is based on the same design choices as AlexNet. So they try to use similar filters with similar configurations. They only try to increase the number of layers in order to improve the results. And they also decided to reduce the size of the convolutional filters in order to be able to train the model slightly faster. So they use only 3x3 convolutions and 2x2 max pooling. And they obtained, so they tried models from 11 layers to 19 layers. And they obtained their best results with a model with 16 layer. Which is perhaps a bit surprising that the deeper model with 19 layers didn't obtain better results. And we will continue this discussion when we discuss about ResNet and discuss why the results start to decrease after about 20 layers. Okay, so this was their best model. They obtained the second best result in the competition. They reduced the top 5 error from 11% to 7.3%. Okay, so now if you look at their architecture, you can see here that what's the size of the activation maps and what is the number of parameters. And one generic observation that is valid also for AlexNet and other architecture is that the number, these are just some statistics about the model. So in order to process one image, you need about 100 megabytes of memory for the forward pass and around 200 megabytes for the backward pass. And the total number of parameters in this network is 140 million. So it has a lot of parameters that require optimization. So it's a very large neural network with millions of parameters. So yeah, I wanted to note that the highest memory consumption is seen in the early convolutional layers, and the highest number of parameters is usually when we connect the convolutional layer with the first fully connected layer. So here most of the parameters, over 100 millions, are only in this fully connected layer. And you can see that actually number of parameters gradually increases to this layer. And as I observed earlier, you see that most of the parameters are in the fully connected layers. So really the convolutional layers are much more efficient. So if you try to imagine a fully connected architecture with the same number of layers that replaces the convolutional layers with fully connected layers, will result in a much larger number of parameters that is very hard to optimize. And yeah, the disadvantage is that these layers have higher memory required to store the activation maps, but still this is not a big issue. Okay, so the ImageNet, the large scale visual recognition challenge. So this is a short ILSVRC. So this actually is the ImageNet competition. So the winner in 2014 was GoogleNet. And GoogleNet proposed a different modular design. And they actually tried to make some design choices matter less. So for example, they first they said, okay, we don't know what's the ideal depth of our network, so we don't know how many layers we should use. So then we use this network and we have the output, I don't know, after about 10 layers, after about 20 layers, and after about 30 layers. So this was the first choice, was to get the final output from different locations, and they use voting of these outputs to obtain the final decisions. And another design choice was to include these inception modules. So the name of the architecture, you'll find it also as GoogleNet and also as InceptionNet, which stems from the name of these inception modules. So again, here the design choice was, okay, maybe we should use 1-on-1 convolutions and then 3-by-3 convolutions, or we should use 1-by-1 convolutions and then 5-by-5. So they tried different choices, and these are alternative pathways that are concatenated here as the output. So this is a modular design. So this allows the network also to learn different pathways, and perhaps I don't know, in this case, suppose that in this location the 1-by-1 convolution, this pathway is not useful, then simply the network can learn weights that are equal to 0, and then this output will not matter here anymore. So yeah, it can strengthen the output for the pathways that are useful and decrease it for the other pathways. So it's kind of also trying to learn the pathways, not only the weights. Okay, so this was, yeah, the architecture proposed by the Google team for the ImageNet competition. They used this configuration in order to reduce the number of weights while increasing the number of layers. So, and they also removed here, they use this average pooling before the output. So This reduces the number of parameters required for the first fully connected layer. So this network is much deeper. We see here the inception module. So this is the input, the several inception modules, and then the output. And we see that the number of parameters is about 5 million. And compared to AlexNet, it has 12 times less parameters, and unfortunately the number of computations is about twice as high, but not as high as the improvement. So the improvement with respect to AlexNet is more than so the error is reduced more than twice, so from 16% to only 6%. Okay, so yeah, this is the last architecture that we're going to discuss, ResNet, which is the winner of the ImageNet competition in 2015. And they obtain a top 5 error rate of 3.6%. So maybe I wasn't clear so far that what's this number. The top 5 error rate is computed as follows. So the model is given a test image as input. It can make 5 predictions, so you can use, I don't know, the classes that have the top 5 probabilities predicted by your model. And if the correct class is among these top 5 predictions, then it is considered as a correct label. Otherwise, the prediction is wrong. So if you do not provide the correct answer in your top 5 predictions, then it is considered an error. Okay, so maybe this seems as an easier evaluation, so it doesn't seem that hard, but it is hard because ImageNet has 1000 object classes, and these are not classes like cat and dog. They are specific races of cats and specific races of dogs, and specific species of birds, and so on. So if you think, I don't know, and there are even classes that perhaps you don't know what they mean. So for a trained human that actually knows a bit about the classes, and actually the trained human, so this experiment was done by Karpathy, which was also one of the authors of the ImageNet paper that introduced the dataset. So he performed this experiment and tried to estimate the classes for a bunch of images, and his performance was around 5 or 6%. And so even for him it wasn't so easy. And yeah, for a non-trained human, I think the error is a bit higher. And actually this ResNet model obtaining an error rate of 3.6%, which is lower than the human level performance, is quite remarkable. Okay, so yeah, so first, I think this is the first model that goes below the human level error. So it is a nice result. And in 2015, and so and also in the objects in context competition, COCO 2015, they also obtained the first results. So they won the ImageNet classification challenge, They won the ImageNet detection challenge, ImageNet localization challenge, COCO detection, and COCO segmentation challenges. So this ResNet architecture was used in all these challenges, and they obtained the first place in all these challenges. So this was a really interesting result, and their main idea was to go deeper with the neural networks, and they managed to train a network with 152 layers. And their result is also remarkable because, as I mentioned, in the VGG group also tried to train deeper models. So when they use the model with 19 layers, they obtain actually lower performance than using 16 layers. And this happens because when you apply the chain rule over several layers, this implies a lot of multiplications, and in the end you will obtain vanishing or exploding gradients, and you will not be able to properly optimize the model. And yeah, the first author of the ResNet residual networks, Kai-Ming He, has also observed this phenomenon. So if you use plain networks with 20 layers, you can obtain this result on. So this is the result on the training. So this is the dashed training, and also you see the result on the validation on the test with solids. So as you increase the depth of the model, you obtain lower results on the test. And they also analyzed the training performance, and they also learned that these models, these deeper models, also provide lower training performance. So this isn't so. Naturally, when you increase the model capacity, you expect the model to overfit more the data, not to do less overfitting. So this is a bit puzzling, and they figure out that this was due to the vanishing or exploding gradients. So then they proposed this modified architecture called residual net, which seems to, so in the training, they observed that when you increase the network size, you get more, you can fit the network better on the training data, and this also brings improvements on the test data. So as you increase the network depth, you also obtain better results on the test data. So how did they manage to do this? They, yeah, this is another slide from their presentation that shows how their network compares in terms with the other models. So this is the AlexNet, this is VGG, and this is ResNet. So it's much deeper. As I said before, the network takes more than 2 weeks to train on a machine with 8 GPUs, but on running time it is faster than VGG, although it has more than 8 times the number of layers. Okay, so their idea was to use these skip connections that allowed so through the skip connection you pass information in both during the forward propagation but also during the backward propagation. So the gradients can also back propagate through these connections, and this allows gradients to travel a shorter path to the input to the layers that are early in the architecture, that are closer to the input, and this allows better training of the network. So the main idea was pretty simple. So when you have let's say two convolutional layers that are succeeded and have the same size of the input and output, you add this skip connection. So here the output in a plane network is denoted by h of x. In this case, for the residual network, the output is given by this function f of x, which is equivalent to the h from the plane network. And we also add here the input from the that goes into the first convolutional layer. So yeah, the main idea is just we have these activation maps that resulted after this layer. We have the activation maps from this layer, and we just add them up using matrix addition, the standard matrix addition operation, and then we apply the ReLU of for this layer. So then we just it's just basically skipping this and adding the components here. So when you do backpropagation, the chain rule will also go through these layers, but also go through this skip connection or residual connection that enforces the gradients at this layer to have values in the desired range. Okay, so this was their main design change, to add this residual connection, and this gives the name of the network residual net. Other modifications, they introduced batch normalization after every convolutional layer. So in order to make sure that they remove exploding or vanishing gradients, they introduced batch normalization. So this is really important for deeper networks. And they also observed that when using batch normalization, they didn't they no longer needed dropout. So their ResNet was trained without a dropout. For initialization, they used the Xavier initialization or Gloro initialization that we proposed, that we presented in the last lecture. They only modified the formula by dividing the standard deviation by 2. They trained with stochastic gradient descent with momentum, just as AlexNet and VGG and previous network architecture. They started with a learning rate of 0.1, which was divided by 10 when the validation error plateaus, so just as other models. They slightly increased the mini batch size, and as I said before, they didn't use any dropout. Okay, another trick that they used in their architecture to reduce the number of parameters was to replace succeeding convolutional layers of 3x3 filters with convolutional layers with 1x1 filters. So these two convolutional layers are replaced with 3 convolutional layers, and these have 1x1 spatial size. So this reduces the number of parameters that are learned, and this trick was actually borrowed from GoogleNet. So GoogleNet has the same idea implemented in the inception modules. Okay, and this is a table that describes the ResNet architecture. So here you see they tried networks with ranging from 18 layers to 152 layers, and actually they even tested the model with 1000 layers. They managed to train it, but they didn't obtain better results than 152 layers. The results were about the same, so it doesn't. They didn't see any practical motivation of using this model in practical applications. So okay, and you can see here. So they use these blocks, these residual blocks in four blocks, and the number of times each block is repeated. So For example, this blocks contains 3 convolutional layers and is repeated 3 times. So this gives 9 convolutional layers, and so on. So this configuration has 50 layers, this one has 101, and so on. Okay, so this was the case study for ResNet. I think we're finishing in time here. So yeah, as a summary, the convolutional neural networks are based on stacking convolutional pooling and fully connected layers. There is a trend towards using smaller filters and deeper architecture, trend towards getting rid of pooling and fully connected layers. So for example, a residual network doesn't have any fully connected layers, just a softmax layer. And yeah, the typical architecture written as a regular expression looks something like this. So we have some convolution and pooling layers that are repeated for a number of times, and then we use a pooling layer. So this is a convolutional block, and the convolutional blocks are repeated for a number of times. Then we have some fully connected layers which might be missing completely, and then we have the softmax classification layer. Okay, so this is the summary. And as I said before, ResNet and GoogleNet challenge this typical regex by using alternative pathways and skip connections and so on. Okay, so this ends. This was the last slides. This ends the lecture. So we still have some time for a couple of questions. So yeah, if you have any questions, just let me know. Yeah, so referring to the early question of Raphael, I think usually you can inspire yourself from these design choices used in VGG, ResNet, and GoogleNet. So I don't know, perhaps a good starting point would be to use a ResNet model, and depending on the complexity of your problem, you can choose perhaps start with a ResNet of 18 layers or 152 and so on. And then you can use more complex architectures like there are even more modern approaches like such as ResNext. So this is one modification, ResNext. And yeah, this is based on using alternative pathways, so it's similar to ResNet. So this was, for example, the model used in, cannot increase it further. So this is the module used in ResNext, and here they try to use this kind of inception model, but with a much larger number of pathways. So it has 32 pathways, but these are actually separated. So you see here that the number of filters and the filter configurations are the same, but they only have a few filters here. So these are more separated. So this seems to be a useful design choice to improve further improve results. Yeah, so there are many architectures out there that you can use as inspiration for your models. Yes, you can use pre-trained models for the Kaggle competition. Yeah, it is possible to do that. I'm not sure that you can use only pre-trained models. Perhaps you need some fine-tuning in order to get better results, but yeah, whatever works for you. So yeah, everything is allowed. for neural networks, no, it is not necessary to preprocess the images. The only type of preprocessing that I discussed last time is you need to perhaps compute the average image and make sure that the images are centered, but this is necessary for AlexNet, VGG, and actually for ResNet this is no longer necessary because you have batch normalization. So essentially, yeah, depending on the architecture, you may need some slight preprocessing, but nothing like, I don't know, handcrafted feature extraction. So the answer is valid for neural networks. If you use a different model, you can use, I don't know, different methods. Yeah, so you don't need to remove the background. You just when you train the network, it should automatically learn to recognize the objects of the interest and automatically ignore the background, so that is not necessary. Okay, are there any other questions? Yeah, the question about so really I think text tokenization is more related to the task and not necessarily related to the model. So yeah, but for text processing you may need some pre-processing of the input. So one way to do this is, for example, to replace the characters with numbers. So you assign numbers to the characters and you replace them with numbers, and then you can apply convolution on top of that. But the convolution should be one-dimensional. So you assume that the input is 1D, so just a sequence of numbers, and then you use one-dimensional convolutions. So you need some pre-processing there, but yeah, it can run on raw text. You don't need to do any pre-processing. So it's maybe more related to the type of approach. So if you're, for example, if you're interested in discriminating based on style of the authors, which means that the style is captured usually by stop words such as the use of words off the earth and so on, then you can just perhaps use the whole input, the raw text. But if you want to, I don't know, to classify text by topics, then you can remove the stop words before giving it as input to the network. So it really depends on the task, and you can try it and see how it works. It's not a generic rule. Okay, so another option would be to use to replace the characters with one-hot encodings. So this is another approach, and you can also use, so this is you can apply CNNs at the character level. So this is the first two approaches that I mentioned so far, and you can also apply them at the word level. So but first you would need to learn some vectorial representation of words. So you can either first transform the words into word embeddings, or you can actually learn an embedding in your network architecture. So you can, I think, frameworks such as Keras have these embedding layer that can be added into the network, and the word embeddings are automatically learned in this layer. And another aspect to consider if you use convolutional neural networks, you need a fixed input size. So you can either consider the maximum length of, let's say, a sentence, and for the output that doesn't reach this length, you can add zeros, so you can zero pad the input, and this is one option. And if a sentence happens to be longer than that, you just trim it out. So this is what people usually do in practice, and they obtain good results. Okay, so I don't see any other questions, but maybe I can wait 1 or 2 more minutes. Okay, so I think this was the last question. So yeah, thank you guys for participating, and see you next week when we will start our discussion about bag of words and a bag of visual words. Okay, so thank you once again.